Okay, hello everyone. So, I'm Alessandro Di Federico. I'm a PhD student at the Politecnico di Milano, and today I'm here to talk about revng, which is the result of the work of my last year of PhD. So, we'll go through a quick introduction, then we'll see a couple of technical things, how we implemented the core features, some of the core features we have, and then we'll see some experimental results, and then we'll go to the conclusion, and we'll have a short demo to show what we're talking about actually works. So first of all, what is revng? Revng is a unified suite of tools for static binary analysis. So static binary analysis, it's basically taking a binary and trying to recover some high-level information just looking at the binary. So we're not running it in any way. And when we talk about the unified static binary analysis tool, we mean something that the analysis that it performs are not dependent on this specific input architecture of the binary that you're giving it. This means that if we, for instance, develop a function boundary recovery analysis, it's supposed to work on all the architecture in the same way. So we don't encode patterns which are specific to a certain architecture or things like this. So far, we have three main features. The core part is the static binary translator. So means take a binary compiled for ARM, let's say MD5 sum, and lift it to some intermediate representation, and then recompile it back to another architecture, say x86-64. Then, from the static analysis point of view, we can recover the control flow graph in a pretty accurate way, and we also recover function boundaries, so try to identify which basic blocks in the binary belong to the same function originally. So the core part is revamb, the static binary translator. And what it does basically consists in, first of all, parsing the header of the binary that you give it, try to load all the segments, identify the executable code, and then the core part, the most important part, is identifying all the basic blocks within the binary. This might seem trivial, but it's not. This is the core part, one of the core parts of our work. Then, for each of the basic blocks that we have been able to identify, we feed them to QEMU. QEMU basically can work as a lifter or as, let's say, a disassembler and output an IR, which is specific to QEMU for each of the basic blocks that we provide him. So raw data, QEMU. Then, since this, in particular, the part of QEMU that we're using to do this is called the tiny code generator. Then, since this IR that QEMU provides, it's very rough and it's not very suitable to perform the analysis that we want to perform, we translate it to LLVM IR. We collect all of these basic blocks in a single function, and then since we are there, what is the most obvious thing that you can do when you're in LLVM? Compile it back. So this is the first thing that we do. This is the core of our tool. Why did we choose QEMU? Well, because QEMU supports a lot of input architectures and basically abstracts all of this architecture into an IR, on the top of which we can build our analysis. So if QEMU supports this architecture, it can work as a front end for us. And then since LLVM IR, on the other hand, supports another set of output architecture, let's say target architectures, basically in revamb, we can combine the benefit of the two. So we take any of the architecture supported by QEMU, we translate a certain binary into an IR, the LLVM IR, and then we can compile back to several architectures. Well, actually, this is in the general idea, but so far we are supporting only MIPS, input, ARM, input, and x86-64, and then we compile back to x86-64. But the general idea of this project is that it should be trivial to add support for another architecture and get the same quality in the results, for instance, in function detection. OK, so before we see an example of going from a basic block to LLVM IR, I want to create in your mind some mapping between some typical concept that you have in assembly and how we handle them in revamb. So a CPU register, its model in our system is a LLVM global variable. A direct branch from basic block A to basic block B is modeled in the same way. So we translate the basic block A, and we emit a direct branch to basic block B. Instead, for indirect branch, it's a bit more complicated, because if our analyses are not able to recover all the possible jump targets, all the possible destinations, we have to jump to a dispatcher. The dispatcher looks like this. It's basically a gigantic switch statement which maps each input program counter, so the starting address of all the basic blocks that we have identified, to the corresponding basic block containing the translated code. So it's a runtime fallback path in case we are not able to statically determine all the possible targets of a branch. And obviously, the bigger this switch statement is, and the more frequently you use it, the more the performance will be affected. So we want to minimize it. And so we want to recover an accurate control flow graph as much as possible. So we have to use this as little as possible. An important thing to note here is the abort. So if we are not able to, at runtime, if a certain program counter is not present in this switch statement, we will fail. So it's vital for us to identify all the basic blocks present in the binary. Otherwise, we will get a runtime failure. So this is the first and foremost objective that we are aiming to, not having a runtime failure, so being able to identify all the basic blocks. Then, for certain complex operations, such as, for instance, floating point division, QEMU does not emit a series of instructions in its own intermediate representation, but emits a call to a C function, basically a function written in C, which implements the behavior of, for instance, floating point division. These kind of functions are called helper functions. Same thing for syscalls. So one of the main advantages of using QEMU is that QEMU has two modes of operation. If you've been using QEMU, you're probably used to the full system emulation mode. So you have basically QEMU emulates for you the whole machine. So I don't know, device drivers and whatnot. It performs the boot and everything. But the part that we're exploiting in this case is the user mode, which allows you to run a single binary compiled for Linux or FreeBSD and run it right away. So for instance, ls or MD5sum. And how does it do that? Well, basically every time a syscall is performed, there's a helper function which handles it, and for instance translates the syscall number for ARM to the corresponding syscall number for the host architecture, and changes the layout of data structure to interface correctly with the operating system, and so on and so forth. So for these two last points, these helper functions, what we do, we basically extract them from QEMU, we compile them to LLVM-IR, and then we'll statically link them into our binary. So our final binary is completely self-contained. OK, let's see an example. So suppose that we have these two instructions. These are ARM assembly. We have load instructions that is writing in the register R3, loading from an address relative to the frame pointer with an offset of 8 bytes. And the second instruction is a branch and link, which is a call instruction, basically, to this address, 0x1234. Let's see how it is expanded by QEMU into its own IR. So basically, here we see that we have a series of very small operations which are RISC-like, and basically the registers are mapped as variables. We have, for instance, here we are loading from the frame pointer into a temporary register in TMP5. Here we are loading another value, which is -8, in another temporary variable. Then we perform the addition. We perform a load from this address, and then we write the result in R3. So this is basically expanding the behavior of a single ARM instruction, basically making all the side effects explicit. What about the branch and link? This is an interesting point, because as you can see here, it's loading a constant value into TMP5 and then putting it into LR. LR is the link register, so where in ARM you save the return address. So in our view, we don't even have the concept of function call with respect to the original architecture. It's abstracted away by QEMU. So later on, we will have to detect that this is a function call by matching this pattern. So you're writing an integer value, which happens to be the next program counter, either to a register or to memory. OK, that for me is a function call. So we are very independent of the input architecture. And then here we are writing the destination address into the program counter, and exit_tb, it's something specific to QEMU we don't care about. In LLVM-IR, it's pretty much similar. So we load from FP, which is a global variable. As we said, registers are mapped to, and in general, all the CPU state is mapped to global variables. We add -8, we convert to a pointer, we perform the load, and we store the result back to R3. OK? Same thing for branch and link, nothing special. We're writing into the global variable corresponding to the link register and to the program counter. OK. So let's see a general overview of the system, how it works. So first of all, you take the binary, and you feed it to the first phase of revamb, which parses the binary, loads it, and first of all tries to collect a first set of jump targets. By jump targets, we basically mean any address, any program counter in the binary where it's possible to jump to. So let's say the starting address of a basic block. So we start to collect a first set of addresses of basic blocks by scanning the global data byte by byte, looking for pointer-sized integers which happen to be looking like pointers to the executable segment, and we record them as jump targets. We obviously also consider entry points, or if you're talking about dynamic libraries, all the exportant function, and so on and so forth. Then we feed all of these jump targets to QEMU, which produces its own IR. And then basically we translate this IR to the LLVM IR. At this point, we generated some code. We go through all of this code and we look if we can find some direct branches to some basic block that we have not translated yet. So we collect new jump targets from the direct jumps. If we have new jump targets, we go back to QEMU and repeat and again and again. Once we cannot find any new additional jump target due to the direct jumps, we perform a series of more expensive analyses to try to recover the jump target, the destination of indirect branches, for instance, due to switch statements. We'll see an example of this in a while. And basically, do we have new jump targets? OK, let's go back to QEMU again. We don't. Then we go to the finalization process, where basically our module is ready, and we can perform some additional analysis. For instance, I try to identify function boundaries. And finally, before emitting the final binary, link in all the helper functions that I was telling you about before, taken from QEMU. And then basically, finally, we can output a binary for any of the architectures compiled for, supported by LLVM. OK, so let's see a couple of interesting technical details about how we're doing this. First, we'll see how to recover the destination address of switch statements. And then we'll see a bit how function detection is implemented. So if you ever had anything to do with ARM, you might have seen something like this. This is the typical implementation, the typical lowering of a switch statement for the ARM architecture. So suppose that in R1, we have the result of the switch expression. So when you have a switch statement, you have an expression on which you're switching on. And first of all, you perform a comparison with the maximum allowed value of the switch. For instance, if there are 5 cases and they are all consecutive, you'll compare it with 5. Then, if the previous comparison gives a result that is less than or equal, ls is a predicate. In ARM, you have predicate execution. ls means less than or equal in an unsigned sense. Then we execute this instruction. So we write to the program counter the current value of the program counter plus R1, which is the result of our switch expression, shifted left of 2 positions. All right? So basically, we're jumping, this instruction is jumping to a program counter, which is the current program counter plus 4, plus 8, plus 12, and so on and so forth. And why is this? Because in ARM, each instruction is 4 bytes long. So we are basically deciding, based on the result of the switch expression, whether we want to jump to here, here, or to the next instructions. Now, our aim in our tool is to be able to enumerate all the possible destination of this instruction in a general way without using pattern matching, without pattern matching this specific behavior, and in a way that is as general as possible. For this reason, we developed what we call the AlwaysR analysis, which AlwaysR stands for offset shifted range. We'll see what's that in a second. And it's basically a data flow analysis aimed at handling switch statements, not only for ARM, but it works very well also in MIPS and x86, 64. What it does basically, it consists in taking each SSA value and try to express it in a relation with respect to another SSA value, which we can call x, plus an offset b, and multiply by a factor b. Moreover, for each basic block, it tries to keep track if this value x is contained within certain boundaries, and whether it's used as a signed integer or an unsigned integer. Now, you might be confused by this, but let's try to summarize this. So, supposing that you have 2 SSA values, x and y, we are trying to express y in terms of x, so y equals a plus b multiplied by x, so we can also say that x is contained in the CD range, or it's outside the CD range. We consider all the two options. And X is signed or unsigned. How can we do this? Let's see an example. So we have the same snippet of code before, and this is how it looks like in our system. So at the center, we have the LLVM IR generated by this snippet. And on the right, we have the pseudo-C, in case you're not familiar with LLVM IR. But if you're not, why are you here? So basically, what it does is it's implementing what those two instructions we're doing. So R1 is our switch expression. We first of all check if it's greater than or equal 4. And if it's the case, then we check if B, which is I minus 4, is equal to 0. So B minus 4 equals to 0 means B equals to 0. And if this condition is false, we exit. So basically, we are saying R1 greater than or equal 4, and it's not equal to 4. So we are saying if it's greater than 4, then exit, which is exactly what the condition, the predicate that I told you before was doing. So it's less than or equal. So if it's greater, we exit. Instead, if it's actually less than or equal, then we take the original value, A, we shift it left of 2 positions, and then we add the current program counter, and we write the result into the program counter. So let's see how OSRA, the OSR analysis, actually handles this situation. So for the first instruction, for %1, we will just associate to it X, because we don't know anything about this instruction. It can be whatever for us. Then the second instruction, %2, basically subtracts 4 from it. And so we associate X minus 4, since this is within our expressive power, within the expressive power of our analysis. Then we have a comparison for greater than or equal 4 with %1, which was X. So basically, we associate to %3 X greater than or equal 4 in an unsigned sense. Then we take this condition, and there is a branch instruction based on this condition. So we propagate this condition to the true branch, and we propagate its negation to the false branch. So in BB2, we will know that X is going to be greater than or equal 4, while in BB3, we will know that it's going to be lower than 4. Then we proceed to BB2, and we check if %2 is equals 0. But if we check what %2 was, X minus 4. So we are saying X minus 4 equals 0. We solve this very simple equation, and we discover that it's actually saying if X is equal 0. Then we have another branch here, and so on the true branch here, we will have to propagate this condition to BB3 again. So in BB3, we will have 2 conditions, X lower than 4 or X equals 4. Then we can merge them because both paths are actually valid, and then we know that in the last basic block, X is going to be lower than 4, lower than or equal to 4 in an unsigned sense. Finally, we take again the original instruction, %1, X, and we multiply by 4, shifting left of 2 positions. Then we add a constant, and this is our final expression. So this is what's being written into the program counter. But since we know that in basic block 3, X is going to be lower than or equal to 4, basically we can enumerate all the possible destination of this jump instruction. And we don't just know that it's going to be lower than or equal to 4, but since it has been used as an unsigned value, we also know that it's going to be greater than or equal to 0, right? So basically, we can brute force this expression with all the possible values, and we get to enumerate all the possible jump targets. And we might, and this is vital to be able to recover all the possible basic blocks and an accurate control flow graph. All right. Now let's move to function detection. For what concerns function detection, basically we developed a series of a technique that aims to avoid using any architecture-specific heuristics. We are using heuristics because sometimes we could debate on some functions whether a certain basic block actually belongs to a function or to another one. But we don't want to use any architecture-specific heuristic, which is what has been done in the past. For instance, it's what IDA does, if you know what IDA Pro is. So what we do basically is something like this. First of all, we have to identify all the function calls and all the return instructions. Because as we said, that concept is not explicit in the IR we get. because it's basically abstracted away when we translate from using QEMU, when using the tiny code generator. So we recover this information by using the pattern that I described before. Then we start to create a first set of what we call the candidate function entry points. So we try to identify all the basic blocks that in a certain way looks to us as possible function entry points. And this initial set contains, obviously, all the basic blocks that are the target of a call or a function call, because this is like a very strong hint that it's going to be a function. But not only that, also all the unused code pointers that we found in global data. And by unused, I mean that while performing the analysis, for instance, as the one that we saw before, we didn't see a certain, for instance, an address that is storing global data as being used, for instance, to implement a jump table of a switch statement in x86-64. So if a certain address happens to be used in a switch statement in an architecture, we ignore it. We do not consider it as a candidate function entry point. But for instance, if there is a virtual table, instead we consider it because it will never be used to be part of the local control flow of a function. Then we also include the code pointers embedded in the code. Sometimes you are maybe if you are initializing a structure with a function pointer, you might materialize the address of the function pointer into the code, and so you have to dig into the code itself to recover it. And then we go to the third phase. Basically, for each candidate function entry point, we compute the set of all the basic blocks that are reachable from this function entry point. And then we perform a final filter over all the function entry or all the candidate that we have. And following these two rules. First of all, we will keep the candidate if it is the target of a function call, because again, it's a very strong hint that it's actually a function, or if it's reached by at least a skipping jump instruction. What is a skipping jump instruction? It's basically a jump instruction, which is not a function call, but it actually suggests you that the target is a function because it's skipping over other functions. What I'm talking about here is basically tail calls. When you have a tail call, you have something that doesn't look like a function call, but instead it is. And how can we detect that? Because it's usually skipping many other functions. So if between the source address and the destination address of a certain jump instruction, there are other functions in the middle, then we consider this as a skipping jump, and we consider the target as a good candidate for being a function. A key point in phase 3, so when we basically enumerate all the basic block reachable from a certain entry point, is to consider in an appropriate way no return functions. For instance, if you're trying to enumerate all the basic blocks belonging to a certain function, and that function calls exit, you do not have to consider as part of that function the basic blocks coming after the exit function call, because that's a no-return function. You'll never get back from that function. So it's vital to recover in an accurate way the no-return functions. And we have basically 3 ways to do this. First, we try to identify syscalls that can kill the process. So for each syscall, we try to identify which syscall number it's being used. And if it maps to, for instance, exit or exit group, we mark the basic block performing the syscall as a killer basic block. Another source of killer basic blocks are infinite loops. An infinite loop, it's really easy to recover from a point of view of a control flow graph, because it's basically a loop without an exit. If this is the case, you can be sure that from that function you will never return. And so we mark all the basic blocks part of that infinite loop as killer basic blocks. Finally, this is typical, this infinite loop thing is typical of the abort function. Usually the abort function is implemented by first trying to raise a signal or doing several stuff, but then as a last resource, as a last chance, if you're really not able to terminate the process, it starts spinning on an infinite loop. The last type of no-return functions that we can detect are the long jump functions. And basically, we identify them because they write to the stack pointer register in a weird way, in the sense that usually you modify the stack by writing their value, which is either relative to the previous value of the stack pointer, or it's a value that you have loaded from the stack itself. If something happens, if you're writing something to the stack pointer in a way that does not resemble one of these 2 ways, we mark this as a long jump. and we mark this as a killer basic block too. So what do we do then? We said that we mark all of these basic blocks as killer basic block. Then we temporarily set all of their basically we take all of these basic blocks and set them to have a single successor, what we call the sink basic block. Then we compute all the basic blocks that are post-dominated by the sink, which means all the basic block that in a way or another will have to end in a no-return basic block. And in this way, we can get back, we can climb back to the control through the control flow graph and get, for instance, to the entry point of the abort, exit, and long jump instructions, and not only consider the basic blocks that we defined as killer initially, and also possibly all the wrappers. And then we can appropriately mark this candidate function entry point as no return and consider this fact while exploring the basic blocks that are reachable by them. OK, let's see some results. So to assess the goodness of our work, we compile core utils for the 3 architecture we support, ARM, MIPS, and x86-64, and we run the test suite. So as you can see, basically we can pass most of the test, from between 80 and 90% of the test. But the key thing here is that the amount of tests that are failing due to a missing missing code, to code that has not been translated. If you remember at the beginning when I said the abort default case for the switch statement composing the dispatcher, it's basically none. There is a small amount in MIPS, which is a corner case that I can discuss if you're interested, but we have plans to solve it. If you're not completely satisfied with the result, consider that even QEMU, if you run the core utils test suite under QEMU, gets slightly better results than us. The tests that are failing, in our case, compared to QEMU, are mainly due to the missing support of multi-threading. Right now, we don't support multi-threading, but I think that we can get to support it using basically making all of our variables thread local storage. That might save us. But we've simply not looked into that yet. For what concerns function detection, basically we compared our approach with IDA, which is the industry standard for static binary analysis, with revng, well, revng it's us, with BAP, which is a tool for static binary analysis developed by QEMU, and with Anger, which is not only static binary analysis, they do also symbolic stuff, developed at UCSB. So as you can see, the first three columns report the percentage of matched functions without looking at the quality of the matching, just to see how many of them we match. As you can see, we are constantly, we're usually better, we are always better than IDA, and so we can recover more functions than IDA. We can at least identify that those are functions. The functions that we are not recognizing, by manual inspection, we identified that they were mostly due to dead code. So code that has been linked in, even if it wasn't necessary. And consider that here we were using the collect garbage linker option. So these are basically functions which escape this kind of optimization. For instance, if they are functions written in assembly, they will not be garbage collected by the linker. And yeah, for what concerns instead the quality of the functions that we recover, we basically took our ground truth by using the symbols present in the binary, so debugging information, and we compare them with the boundaries that we detected. And then we computed the Jacquard index. So if we have extra basic blocks, the Jacquard index will go down. If we have missing basic blocks, the Jacquard index will go down again. As you can see, we are very close to IDA, which is the one performing best. But the point is that IDA, where it performs better than us, is because it's using some heuristics that are architecture-specific and that we could implement pretty easily, but we didn't want to just to see how far we could push it without using an architecture-specific technique. And as you can see, we are constantly better than BAP and Anger. OK, so far we basically have our tool working on statically linked ELF binaries, so supporting dynamically linked binaries is something we want to do. This might seem like a limitation, but actually Having statically linked binaries means that you have less information and that you are embedding the C standard library, which includes the most difficult code to analyze, because it's often handwritten, highly optimized, and so on and so forth. We support ARM, MIPS, and x86-64. We want to add many more architectures. And we've been working with UClibc and Muscle. For what concerns future works, we plan to implement calling convention detection, so automatically detect the calling convention and perform some stack analysis to improve our results, in particular those that 0.7% of failures in MIPS that we saw before. Add support for multi-threading and try to upstream our changes to QEMU. Because apparently there's many people who want something that, given a basic block, can give you out some intermediate representation. And since it's a common need, it might be interesting to try to upstream it to the QEMU project. Then obviously, something that it's interesting to do is to measure the performance of the code that we emit compared to native or compared to QEMU. And this is in progress. We're working on making it work with the spec benchmarks. But the general idea is that if here is QEMU, dynamic binary translation, and here is native code, we are somewhere in the middle. And being better than QEMU allows us to try to, in terms of performance, allows us to try to replace it where it's being used, for instance, for instrumentation. For instance, I don't know if you know about AFL, the American fuzzy loop. It has a black box mode which uses, which basically allows it to fuzz binaries for which you don't have the source code of, and it uses QEMU. If we can make it work with our tool and we get better performances, you can fuzz software in a faster way, and you might get some other bugs that you were not able to get before. OK, so let's see now a quick demo, just to show you that it actually works. So here we have a file, hello.c. It's basically a very simple hello world. We can compile it for ARM using a toolchain that we compiled, and we link it statically. I can show you that this binary actually works by running it under QEMU. This is QEMU in user mode. It prints hello world. We can try to translate it. This is our tool. It's going to do it. It's going to take a second. Here it's collecting all the basic block, translating, performing the more expensive analysis. It was able to collect some new jump targets due to indirect branches. Doing it again. OK, we found all the jump targets. And now it's linking. OK, and now it produced a binary called hello.translated. And if you run it, it works. Nice thing, you can run it under GDB. We can put a breakpoint on root, which is the name of the function that collects all the basic block. We can run it. And we can step through the LLVM IR, which is pretty nice. So the flickering is due to GDB being buggy. But basically, we can step through the LLVM IR that we generated. To show that we did something actually more, let's say, real world, here I have the binary for ls. So for instance, I can run it with L. It takes a while, but if we try to run the optimized version, so this is being optimized with LLC and OPT with -02, it's pretty much faster. So we can measure the time of the non-optimized version. It takes half a second. If we run the optimized version, it takes way less. And yeah, that's basically all. If you want to know more, just go to rev.ng. The code is available right now. You can try it. And thanks for your attention. I'm happy to take questions.
Hi, this looks really interesting, and I walked in late, so I apologize if you covered this in the beginning. Are you using QEMU because there's no way to get binaries into LLVM IR natively with the LLVM framework? And second part, if you're translating between architectures with different sizes, like a different size architecture like ARM32 and x86-64, how do you handle pointers to memory?
Okay. So for the first question, yeah, from LLVM IR, I mean, there's no way using just LLVM to obtain LLVM IR starting from row bytes, right? I mean, there is the disassembler, but that just prints out, disassembles the instruction. It doesn't give you, it doesn't make explicit what a certain instruction is doing. So QEMU does this for us, and it does it for a lot of architectures. For instance, the Anger guys, they use VEX, which is the Valgrind thing, and it's pretty much similar. But yeah, we need something to act as a front end for us. And using QEMU is also good because it's very future-proof. Sometimes we have features implemented in QEMU even before they have been released on the market, because it's good for testing. They have, for instance, support for modern architectures, so for architectures really recent, like RISC-V. So I think it's a good choice. For the second question, what was the second question? Yeah, okay, basically, the idea is that the user space, the address space is, if you are on x86-64 and you are emulating, you're translating a 32-bit architecture, you'll just be stuck within the first 4 gigabytes of RAM. That's all. So the address, when you perform a load, will be 64 bits, but you'll be just working in the first 200 to 4 gigabytes of RAM. That's basically all. And for the rest, for what concerns the pointers within the program itself, they will be just represented as int32 data types, so nothing special.
Hi, I'm Sandeep. So first question is, you said that you use QEMU to convert x86 to IR. So haven't you tried other solutions like Dagger or LLBT or Maxima to get the LLVM IR? That is first question. The second question is, have you tried your result with any of the dynamic binary translators? There are a couple like BitBlaze or rev.ng.
So rev.ng has been mentioned before, but I've never heard of it. But the dynamic part, I mean, doing dynamic binary translation is a completely different topic, because you have much more information, but it's harder to cover all of it, right? Because you might not be able to run into certain parts of the code, and it takes more time. So what I'm focusing on is the static part. And instead, for the first question, what was it again? No, we just chose, Maxima is the one done by the Trail of Bits guys. Yeah, so that one supports only x86-64. Instead, QEMU is the option that I'm pretty sure gives us the largest support of architecture. It's more future-proof and so on and so forth. But sure, we could use different front ends for our tool. In fact, I think the most important thing is more the analysis that we're writing to recover all the basic blocks, to recover function boundaries in an accurate way, than the only translation thing. I know that for people, this is probably the most fascinating part, but it's not the hardest one. It's a couple of kilobytes to translate from that one from QEMU IR to LLVM IR. So yeah, sure, we could. And maybe one day we'll add support for the VEX IR. But you know, QEMU gives us a pretty large support of architectures, so we don't have a strong reason to switch to something else.
Okay,
and also, the thing with Maxima was that, for instance, they rely on IDA to recover the control flow graph instead. So they just did the first part, not all the rest, at least that I know.
Okay, one more quick question. I think you had one.
Well, I had two, but all right. Let's see if you can one or two. Hey, so first question, do you have to do anything special for C++ exceptions, or do you handle them at all? And the second one is, what is the largest application that you've tried?
So for C++, no, for C++, I don't think we have to do anything special. So right now we're working on supporting spec, which contains C++ code.
I'm talking about exceptions in C++ exceptions. So
exceptions, sorry.
Yeah, sorry.
Yeah, in C++ exceptions, honestly, we haven't been looking into that, but they might give some problems. But for instance, I think they might be recognized as some functions, some parts of the code might be recognized as no-return functions. But honestly, I could tell you something, but we haven't looked into that. But I don't see why, for instance, on the basic block recovery part, why we wouldn't be able to recover them. Somewhere the address of the code handling the exception will be
Well,
written.
they do comparison. Okay, sorry.
Sure.
Yeah, so if you have any other questions, I'm sure the speaker would be happy to speak offline. Let's thank our speaker again.
Thank you.